Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, grade 12s. Welcome once again to the session. Okay, mock exams are fastly actually approaching. It's on our doorstep. Okay, in about 2 or 3 weeks we hit the exam halls. Okay, and the section I want to just go through now is optical phenomena and properties of materials, otherwise known as the main section of photoelectric effect, which is what is taught in matric formally. Coming out of grade 10 and 11, we've come through optical phenomena. We've looked at electromagnetic radiation. We all should be, of course, familiar with the electromagnetic spectrum. Any textbook should house the electromagnetic spectrum. Okay, we know that wavelength, obviously lambda, radio waves, 10 to the power 4. Okay, it's the longest radio wave. Gamma rays, which is 10 to the negative 12's shortest wavelength, but the highest frequency. Radio waves is the longest wavelength wave, but it's a lower frequency. Okay, we all should understand that. Okay, we all should be familiar again with the formula C is equal to F times lambda, C being, of course, the speed of light, or the speed of light in a vacuum, or electromagnetic radiation waves in a vacuum, which is 3 times 10 to the power of 8 meters per second. Okay, we all should be familiar with that formula. Okay, we observe that under the electromagnetic spectrum that radiation is emitted like waves and transmitted through space like waves. So we understand something called wave nature is introduced. And that radiation also displays such a thing called particle behavior. Now, under this thing called the photoelectric effect, we are introduced to a constant by the name of Planck. Okay, because Planck's constant, which is the formula which we'll get to a little bit later, when understanding particle nature, says that it behaves as if there's like packets of energy. Light obviously is able to display like packets of energy called photons. Okay, like photo with ns at the end, called photons, and that packets of energy. Okay, and we get that energy by formula E is equal to H times F, which I'll get through in just like a couple of minutes. I think I'm like almost there. Okay, Planck's constants, he introduced or studied something that's called quantum theory. Max Planck, Professor Max Planck. It's not a history lesson, so I can't actually give you like, you know, the ins and outs or the gists of this man or whatever, but don't worry about it. Anyway, introducing the concept of photoelectric effect. Photoelectric effect, okay, is the process whereby electrons are emitted from a surface of a metal or metal surface when light or electromagnetic radiation of a suitable frequency is incident or is shone on that surface. Incident on that surface or is shone on that surface. Okay, so what we're trying to study is how light, once it's shone or incident on a metal, is able to emit an electron off that surface of a metal. Okay, and that's what we are trying to basically study and what we are trying to basically find out. Okay, which brings in the quantum theory, which basically illustrates the particle nature of light, which we bring in a formula that those of us that are covering this topic in school will kind of know. E is equal to HF, okay, where H is equal to, it's quite a big number, 6,63 times 10 to the power of negative 34 joules per second, which is basically known as Planck's constant. Now, I can always spell this guy's surname wrong. There we go. Planck's constant, which will be supplied on a formula sheet, if they still do that. I know in my day they used to. Where F, of course, is the frequency. We should remember this from grade 10 when we did wave, sound, and light. Okay. Now, of course, we know what frequency is equal to. We can get multiple formulae all right, from this formula, we also know that C is equal to F times lambda, correct? And if we must formulate this, we'll basically get a formula that the frequency of light would be C divided by lambda, correct? So therefore we form a new formula, or another format, formula 1.2 of this formula, that E can also be equal to Planck's constant multiplied by the speed of light divided by the wavelength. Okay, so that's formula 1.2. However, there are more. Okay. The photoelectric effect can be explained by the quantum theory as follows. So when light, or when a packet of energy from light, which is called a photon, okay, with energy equal to h times f, strikes a metal surface, all the energy of the photon will be transferred to the what? To the electron. Now, a photon must have a certain minimum amount of energy to overcome the force of attraction between the metal and electron. That we do understand. We've been dealing with this in chemistry as well, okay, as well as under electrostatics. We know about electrons. They are obviously can be transferred in metal, but under electrostatics, we learned about force of attraction and repulsion. So what the photoelectric effect is saying, that a photon, which is a packet of light energy, okay, must have a certain minimum amount of energy to overcome the force. Anything less than that, it will not overcome the forces of attraction, okay, between the metal and the electron will obviously not budge. But if it has that certain minimum energy to overcome the force of attraction, the electron will obviously be removed from the surface. And that minimum energy is called W0, which is known as the work function. Now, someone mentioned to me earlier that they were revising work energy theorem. It's no stranger that we see the word work there. It's exactly the same thing. It refers to energy. Okay. So the minimum energy would be the work function W0 of the metal. Okay. And any electron that is moved is called photoelectron. Now we need to define what the work function is. Okay. By definition, the work function is known as the minimum energy that an electron in the metal needs to be emitted from the surface of the metal, or from the metal surface. Alright, that's the work function. Okay. Now each metal has its own unique work function. Okay. I'm not going to give you all those lists right now. Okay. But basically, if we want to work this out, okay, we have a formula saying that the energy of a photon, which is E, so energy of a photon, try to fit this in one line, I don't think so, is basically equal to the work function, which I'm going to equate to W0, because that's what it is, W0, plus the kinetic energy, all right, of a photoelectron. Okay. Basically, energy of a photon is going to be equal to, E is equal to W0 plus EK, but E is also equal to HF. So Planck's constant times the frequency is equal to the work function plus the kinetic energy. So that's obviously half mv squared, which is the kinetic energy of the photoelectron to be obviously be emitted from the surface of the metal. So of course, on the side here, quickly, side note, if the energy, all right, of a photon is less than the work function, Okay, that means that the photon does not have enough energy to emit an electron. So the electron's not going to move. If the energy is equal to the work function, the photon has the exact amount of energy needed to emit one electron from the surface of a metal. But if, remember this equates to E, the energy of a photon is greater than that of the work function, the energy that is transferred to the electron is more than what is necessary. The extra energy is now known or converted to be the kinetic energy, okay, with which the photoelectron will exit the surface of a metal from. That's why we have this formula, that if this is the case, we have some extra kinetic energy in the mix. Okay. Now, just as though we have the work function, which is the minimum energy required, we also have another term that is known as threshold frequency. Okay, what is threshold frequency? Threshold frequency, right, of a metal, okay, is also the minimum frequency. The minimum frequency of light that is needed to emit electrons from the surface of a metal. So as much as we need minimum energy to do so, we also need the minimum frequency. All right? Because obviously light works with frequency. Okay? So in other words, we're saying that light or electromagnetic radiation that shines on a metal must have a certain minimum frequency to cause the emission of electrons from that metal. Okay? And that's called threshold frequency. Another term is called, oh, and by the way, this will be referred to as F0. W0 being work function, F0 being the, sorry, well, I lost the word now, I lost the term. Threshold frequency. Okay, cool. And of course, that'll be equal to the work function. So we form a new formula coming up here. W0 will equal to obviously H times F0. Okay, so if you Planck's constant time the threshold frequency will also determine the work function for us. Okay, let's just put that in a box. There's another term that's called lambda 0, which is known as cutoff wavelength. This formula is not given to you in your formula sheet. Okay, cutoff wavelength. Okay, now cutoff wavelength of a metal, what this is, okay, this is the maximum or longest, okay, maximum or longest wavelength at which light photons can emit photoelectrons. Alright, from a specific metal surface, new formula loading, let's do it in orange. The cutoff wavelength, lambda 0, is going to equal C over F0. Speed of light divided by the threshold frequency will give you what is the cutoff wavelength. Okay. Not often used, but still quite useful. I think I used it in my final paper. Okay. Then we have, of course, one more formula, which will be the maximum kinetic energy of photoelectrons. Okay, that formula is basically just rearranged to as follows. Let me just find another layer here. Oh, come on, don't be mean. There we go. All right. So obviously we had this formula, E is equal to the work function plus EK, or EK max. Okay, so the maximum kinetic energy is obviously if the energy of a photon is greater than the work function, the emitted photoelectron will obviously obtain additional kinetic energy. So then therefore EK max will equal to, of course, the work or E in this case, that will go over there, and doesn't really matter, to be honest. E minus the work function, okay, which is basically also HF minus the work function. Okay, that will determine what is your maximum kinetic energy that is obtained, extra energy, especially if, since this will be greater than your work function. Okay. And that pretty much wraps up all the important stuff that is to know with photoelectric effect. Okay, all the important stuff. The only thing that's left to do, of course, is to go through some exercise questions. Okay, and yeah, that'll pretty much sum up the photoelectric effect in one go. Okay. Alright, I only have 8 minutes left of the session, but let's have a look here. We've got a potassium metal plate irradiated with a light of wavelength 5 times 10 to the negative 7 meters. In an arrangement as shown below, the threshold frequency of potassium is 5,55 times 10 to the 14 hertz. Okay, we don't have to define the term threshold frequency, but we can calculate the energy of a photon incident on the metal plates. We could take 3 minutes for that, and we'll go through that question afterwards. Okay, so that was the paper May-June 2019, Adult Matric, paper 1. And you see it's the final paper of an exam, and it's about 12 marks, sometimes 13 or 14. I don't think it's less than 10. So with the formula there for calculating, of course, the energy is obviously just E is equal to HF, or we can go straight to H times C divided by lambda. Okay, so we'll have Planck's constant, which is 6,63 times 10 to the negative 34. Okay, I'm so sorry, where is my color? There we go, all over the lambda, which was 5 times 10 to the negative 7 meters. And of course the speed of light there is 3 times 10 to the 8, sorry, meters per second. And if we do that on a calculator, we'll get an answer of 3,98 times 10 to the power of negative 19 joules. Okay, that was easy. That stuff we've practiced through already, so we should be able to understand that, and we should be able to do that. Okay, you could have split it up. You could have first calculated this in a separate equation to get the frequency first, and then plugged it in here. Still would have got you the same answer. Okay, so it doesn't really matter, of course. Thank you, Matrix, for joining me this evening. Unfortunately, time ran out on us, so we could not finish the rest of the question, but 10.2 covering through the fundamentals of what we learned tonight, how to calculate the energy of a photon to move a electron off the surface of a metal. This is photoelectric effect in essence all wrapped up. We will visit this again when we touch on revision before finals of this year 2021. Have a great one. Please don't forget to like this video, comment on it as well as subscribe to our channel, Good Better Best online videos.